All right, welcome to day 8 of our environmental data science class. We're going to continue working with the Lagos data today, and instead of just working with the spatial data, we're going to start blending together spatial data and actual sort of lake water quality data. So this is the sort of first script we made. We're going to go ahead and make a new one. So we'll go File, New File, R Markdown, and we'll call this Seki, we'll call it Lake Water Quality Analysis. And we'll keep it as an HTML. And then I'm just going to save it right away as to link WQ analysis. I'm going to delete all this stuff. The very first things we're going to do are going to look a lot like what we did last time. So we're going to load the required packages, and we're going to load in the Lagos data sets. So let's go ahead and copy that, paste it over here. And that's all true still. So in Lagos, here we grabbed spatial data when we did the Lagos locus, if you remember. I'm just going to run this code chunk because it takes a second to load all that Lagos data. But in this data set, there's also this sort of data structure, data frame that is called epi-neutr. So let's say names Lagos. So this is the full data set. And there's all these different things. And what I want to focus on here is this data set called epi-neutr. And what's in there is a bunch of nutrient data and epilimnetic data, so data on the sort of water quality in the lake. And so we'll just call it nutrient data. And we're going to do Lagos. And then to grab that data, we just use the $, and we'll use this. And so now we'll have this new data frame. So instead of grabbing the locus data, the lake centroid information, we're going to say we're going to grab the water quality data. And then, we might want to take a look at that data. So let's go ahead and do a names nutrient. So this is all the column names. You can see it's a very wide data set. Column names. And it has all these different columns. So it's like, what's the Lagos ID, program ID, the sample date, the program name. So this is who took the water quality information. There's over 400 programs that take that. And then we start to get into things that we kind of understand as water quality parameters. So this is chlorophyll A, which is correlated with the total amount of algae in a lake. This is DOC down here. So that's dissolved organic carbon. That's sort of an indicator of how much, obviously, carbon is in the lake. And then there's another one way down here, which is Seki. And Seki is sort of the total amount of Seki, or the total depth at which you can still see a disk. Seki disk depth is one of the oldest ways we've ever measured water quality. And for this class, we're just going to focus on Seki, DOC, and chlorophyll A. And you'll notice that there's a lot of other information per group. So there's chlorophyll A, and then there's chlorophyll A quality. So there's chlorophyll A sensor code, detection limit, lab method name. So this is just making sure that when you're comparing across maybe the Iowa State Department of Health, Public Health takes chlorophyll A in a certain way, and the Minnesota State Department of Public Health takes it in a different way. You want to make sure that you're comparing across the same ones. For this particular exercise, we're going to ignore all that. We're just going to use all the chlorophyll A data in here and all the DOC data and all the Seki disk data. So we'll sort of just assume that they're high enough quality. Again, if you're doing this for a full analysis, you would definitely want to check out the quality information that goes with this data set. Okay, so now we have this new data set called nutrition, or nutrients rather. And the first thing I want to do is just subset that to make it a little bit smaller and more understandable. So I'm going to just add a new code chunk. I just hit Control-Alt-I, and then I'm going to say subset nutrient to only keep key info that we want. So now I have, to subset that, I'm going to subset the columns. So to be clear, I'm not subsetting data just yet. So this will be an example where we use the select function. So we'll say maybe clarity only. So chlorophyll A, total carbon, and Seki disk depth are all parameters that indicate the clarity of the water. So they all control the clarity to some degree. So chlorophyll A and absorbs light. DOC can also absorb light, and those two together contribute to the Secchi depth, along with inorganic sediment, which we don't have that information in Lagos just yet. So I'm going to go ahead and say here, and then I'm going to select the column names that I want. So we definitely want to keep the Lagos Lake ID. We definitely want to keep chlorophyll A. We'll keep DOC, Secchi. We probably want to keep sample date. And I'm just going to quickly scan through, and that says sample date, which to me says it probably doesn't have time stamps. It just has the date. So we'll assume that it's just a daily estimate, not sort of hourly. So we'll have just sample date. And just to keep it sort of a little clearer, I'm actually going to put that here so that we start out seeing Lagos, Lake ID, sample date, chlorophyll A, DOC, and Secchi, because that'll be the order that this is arranged in. So now if we look at the top of clarity only, oh, it's not a tibble yet, so it printed infinity. So since it's not a tibble, we can do clarity only, just the head. And so we have these Lagos Lake IDs, sample date, lots of NAs here, and then chlorophyll A, DOC, Secchi. I'm a little worried about all those NAs and sample date. I'm going to do a summary, clarity only, just to see what's in there. So sample date is completely empty. That seems like maybe that's a Lagos error. Let's see. You know what? I might have to get load in a different version. So I'm going to go to Lagos ne/git and I want to check out which version name I should be loading. So maybe I'll do Lagos ne load. It seems like there's an error that we just discovered live. So instead of loading 1.087.3, we're going to load this one, 0.1, which I have used before and I know has sample date. So let's see if that changes the outcome of this little exercise. Okay, well that takes a lot less long to load. And then now we'll just do the same summary call. Yeah, okay, great. We have a bunch of data. Unfortunately, it looks like it's coming in as a factor, which we do not want dates to come in as a factor. So we'll go ahead and change that. So we'll do sample date equals as dot character sample date. So now we're making it a character. And then we can just take a look at this. And this looks like month, day, year to me. So we can go back up to our packages, load the package lubridate. It's an easy way to deal with time. And then we'll go back down. And once this is a character, we can actually directly convert it to a date that R knows is a date. So here it just thinks it's a factor or a character, so it's not reading it as an actual date. So what we'll do is pipe this character forward to a command called year or month, day, year. And that gives us month, day, year. And so it's going to read all these and it's going to interpret them as dates. So we'll just do month, day, year, and then a dot. And that just means, hey, the previous thing, which is now a character, I'm going to convert to a date. So let's rerun this. Oh, I didn't rerun the lubridate line. So now lubridate's loaded, so that should work. Okay, great. And now if we do summary clarity only, when we look at that, instead of printing a bunch of factors, it's going to actually print the sort of earliest time that someone took a sample in the latest, which is 2003. That's because I'm using an old version of Lagos, I think. Okay, so now we have all the information we want. Right now, none of this nutrition data is spatial, right? So we have all this information, but it's totally not spatial. So let's go ahead and see if we can sort of do some subsetting on this data set and then join it to the spatial data. That'll be sort of the main exercise of the day. And so we can plot data and look at like what's the average chlorophyll A across the country. Or across the Northeast at least. So let's go ahead and do some subsetting. So let's say, let's only keep sites with at least 1,000 or 100 observations. And that number might change depending on what is the outcome, because I just kind of want to make sure that we're not working with too many sites with relatively little data observations. So to do that, we can do a count clarity. So now we're going to just say we want to know how many observations are in each of these data sets. And if we look at the data, we have a lot of chlorophyll A data because there's only 80,000 NAs. We have far less DOC data because there's 258,000 NAs. And we have the most of SecuDist data, so there's a lot more data there. So maybe when we're thinking about counting the number of observations, maybe we'll just ignore the DOC and we'll just keep observations that have both that have observations of both chlorophyll A and SecuDist depth. So let's say we're going to just take counts of that. So to do that, we take clarity only, and then we're going to filter the times that we do not have information on chlorophyll A. So we'll say is.na chlorophyll A, and then again is.na seci. We'll keep all the ones with DOC, and that'll do both. If there's it'll erase a row if there's a chlorophyll A NA and a seci NA. So you have to have this will give us full information. And then we can do a group by, or actually first let's just, we can look at the number of rows in a data set by doing n-row clarity only. And I'll just comment that at the number of rows. And then in the top right, you can always see that too. It's 289,000 observations of 5 variables. That's over here in the top right. And then when we do n-row, it gives us that same number of observations. So we can look at the number of rows. And then now we just want to check how many we lose when we set this new condition of only wanting full data sets. So we'll do count clarity. And then you can just look over in the top right. We lost about 100,000 observations, but you could also do something like n-row clarity only. So the previous one minus n-row count clarity. And then I'll just say how many observations did we lose? And then I'll drop that. And now I'm realizing I don't like the name of that, so I'm going to change it to chlorophyll A seci, because that's the ones that I'm keeping all the data. And then I need to change this, so if you comment it out, it works. One thing to know is if I'm coding a lot of lines like this, you can use Control-Shift-C to comment or uncomment many lines at the same time. So if I wanted to not run this code and comment it out, I can just use Control-Shift-C. On a Mac, I think that would be Command-Shift-C. So we're not going to look at that, but we lost about 100,000 observations. And then we'll say chlorophyll A seci at least 100, so we'll just call it 100. And then we'll do clarity only. And then we'll do group by Lagos Lake ID, so each of these has an ID. And then we'll do a mutate, and we'll do count equals n. And then we'll do a filter count is greater than 100. And here I bet we're going to lose a lot of observations. So again, just sort of pay attention to the top right. How many do we keep? Chlorophyll A seci at least 100. Wow, we only lose 60,000. So maybe 100 observations isn't quite strict enough of a filter. So I'm going to go ahead and change this to 1,000 because I don't want to keep that. I want to keep only a few sites really. And so we'll call this, we'll change the name here to 1,000, and then we'll change the condition down here to 1,000. And let's go ahead and run that. And hopefully we're left with a lot less sites. Yeah, so that's only 4,200 observations. And so when we do that, let's see, we can do, maybe we want to look at the number of unique sites. So we can do a length, unique, chlorophyll A, seci, 1,000. And then we'll do Lagos Lake IDs. And let's see how many that is. Okay, so now what I've just accidentally did is I kept only 2 sites, and those sites just have these 4,000 observations. So we dropped too many lakes with this new condition. So maybe instead of 100 and not 1,000, we'll try 200. And we'll go up and make sure that this is true. And we can go here, just make sure that we're getting it right. And then now we want to check the length on this new condition of 200. Okay, so we keep 200 lakes. That's about what I wanted. Okay, so now we have 200 lakes that have at least 200 observations. Keep only at least 200 observations of Secchi and chlorophyll A. And together, those are a total of 62,000 observations. So some of these lakes have far more than just 200 observations. Okay. And if we wanted to sort of take a look at this, how many observations each lake has, we can do a summary on 200. We can sort of look at the count over here in the bottom right. And we can see that the minimum is 201, which makes sense. That's the condition we set. And then the first quantile is 236, median is 269, the mean is 501, and then there's one lake with over 3,000 observations, which is a lot. Okay, so now we've subsetted this data set. Again, we're sort of not working in spatial data yet. So within these data sets where we have a lot of information, now we want to make sure we can join this to our spatial data set and then plot where we have this data. So let's say join water quality data to spatial data. And here we want to only keep sites that are in both the chlorophyll A Secchi 200 and in the Lagos or the lake centers. So we're going to do an inner join where both of them have the full data set. So we'll say spatial chlorophyll A. I'm going to call it just spatial 200. The sort of information upstream hopefully tells you what that is. And we'll do an inner join. And the two data sets we're joining are chlorophyll A Secchi 200 and lake centers. And then what that does, we want to make sure we do it by Lagos lake ID. So we've kept that, spatial 200. And then we want to just make sure that that works. One thing I've done on accident here is I've kept all 62,000 observations, but really I just want this to be a sort of index of the sites. So to fix that, we can take chlorophyll A Secchi 200 and we can use this command called distinct. And we're going to do Lagos lake ID. And then we can say keep all, so we'll keep all the columns that come with that. But what distinct does is it says, okay, how many unique or distinct lake IDs are there? And we just saw earlier that there's 201. And so now when we join it, we should only get out 201 lakes. Okay, and indeed, when we do in row spatial 200, we get 201 lakes. Great. So now let's go ahead and map those lakes, see where they are. Oh, that's because I haven't made this a spatial object yet. So I'll take some code from over here where we did that. And I'm going to make it spatial lakes instead. I'll go ahead and put that in this top line. Make NSF object. So here's where we're making the lake centers NSF object using the Latin long information. We're going to transform it to make it an equal area projection like I talked about in the last video. Actually, I'm going to drop that because it's going to plot faster if I don't have it. So we'll just do spatial lakes. And now instead of joining to spatial lakes, we're going to just join to lake centers. And now when I use the map view, it should work. And if you notice this error command, it's super helpful. It says error, oops, arguments x colon or y colon are missing. You probably expected spatial 200 to be a spatial object. However, it is a class of grouped data frame. So it wasn't yet a spatial object. So now when we do the map view, we're still losing. I think I might have to change the order. So it's, I think the order of these matters. So this will keep the spatial information if I do this, hopefully. Yep. And so that was just because I had to have this first, because I had to say, hey, I want this to be a spatial object, not the second one, which was the grouped data frame. Okay, and so here's the states where we have at least 200 observations, and here are the lakes where they are. Many of them, I'm guessing, are going to be reservoirs. So that looks like it's sort of in a reservoir area. You can see these are still doing lake centroids, so it's like doing the center of this whole lake / reservoir, and the center of it is sort of not actually in the lake. If we go up to Minnesota, we'll find that in a regular lake it is actually in the center, hopefully. Yeah. Great. Okay, so now we have this sort of Lagos Lake data. And what we're going to need, the sort of final step is maybe we want to look at the mean chlorophyll A concentration and mean Secchi depth across the country. So we'll do mean chlorophyll A. So, these are sites with a lot of chlorophyll A information. It'd be nice to see if there's a sort of spatial distribution of chlorophyll A. And to do that, we just need to say mean values. And we'll say 200 just to indicate that the threshold was 200. And then here we're going to take the mean of this chlorophyll A Secchi 200. And we'll do, these should be already grouped, but I'll just make sure I'm doing it right. I'll say lake ID just to make sure. And then I'm going to do summarize mean chlor equals mean of chlorophyll. And I'll do that works. And then I can also do the mean Secchi equals mean Secchi. And I missed that, so let's run that. And this should be 201 observations because we have 201 sites. Mean value is 201, great. And then what we want to do is now join that to the spatial data set. So we'll take this line, mean spatial. We're going to interjoin spatial lakes. Now, instead of doing this distinct call, we're going to just do the mean values 200. We're doing it by lake ID. And then now we can do a map view of mean spatial. Z-call equals chlorophyll A. So this is going to, mean chlorophyll. So this map is going to do a heat map. Breaks are not unique. Let's check out what the structure of mean values 200 is for the summary. So we have some NAs in there. I wonder if we do NA. So that when you take a mean of an observation, you can do NA remove equals true. And that'll say basically if there's any NAs in observations, just ignore them, which is dangerous and something you should consider when you're doing it with your real data. Somehow we kept some NAs. I think when I'm joining here, I might be creating NAs. Although I don't quite know how NAs are getting through that. So what we'll do is filter is.NA mean chlorophyll is.NA mean Secchi. And again, removing NAs comes with its own sort of, it's a decision you should be making. For this purpose, I'm just trying to get the plot to generate, so I'm getting rid of the NAs. And now when I do summary, I should have no NAs, which is good. And then when I do the map view, it should work. And indeed it does. It looks like this random lake, there's no sort of obvious spatial distribution to me here. Maybe the Northeast is less, has less algae blooms, less chlorophyll A than the sort of lakes region of the Midwest. One thing we can do to sort of make this a little more visible is maybe we can do the log 10 chlorophyll mean. And so we'll just do log 10. Oops, should not use that assignment now. Log 10 mean chlor. And then we'll do mean spatial again. And instead of coloring it by the mean chlorophyll, we're going to color it by the log base 10 of the mean chlorophyll, just to see if we can, if the pattern pops out anymore. To me, it doesn't. Again, the Northeast sort of looks more clear water, which I think would probably be true. And the sort of Midwest, and particularly these reservoirs, look to be a little bit more prone to having a higher mean chlorophyll A concentration. Okay, so that's all I really wanted to get through today. We wanted to sort of move between spatial analysis and regular data frame analysis. See you in class.